Karoni, a security researcher at Appdome, and today I'm going to talk about leveraging the Mach-O format and the iOS dynamic linker for advanced injection techniques and research. Before we're going to start, I want you to take a look at this code and try to understand what it does. And more important, how can you bypass this specific check? I'll take you a few minutes to look at it. If you succeed, it's great, but if you don't, I promise you until the end of the presentation, you will. So, the goal of this presentation is we'll start actually to talk about a short brief about the Mach-O format and dyld, the iOS dynamic linker, and see how malicious actors can use some legitimate functionalities of dyld for offensive concepts. In addition, continue and I'll provide some key to improve debugging and research methodologies, and of course, ends up with mitigations and recommendations. So, raise your hands if you are familiar with iOS, macOS, or Mach-O formats. Well, great, then I'll explain everything. Okay, so the Mach-O format is the standard library format for executables and libraries in iOS and macOS. It's designed for efficient loading and execution across various architectures. It contains of the Mach header, load commands, segments, and sections, which contains actually the code data and metadata that the operating system and specifically the dynamic linker is used for not only running the application, then the main binary, and all its dependent libraries. Some of the static analysis tools that we'll see also in these presentations are Mach-O View, IDEPRO, O-Tool, we have also the J-Tool, and we'll see several of users with those tools in addition for inspecting Mach-O binaries. Well, let's dive into how dyld, the dynamic linker, use this information to load and link application at runtime and see what happens actually when you click an application. Okay, so the linker's job is to seek symbols and libraries dependencies and actually resolve them and load. Dylds do it by loading the executable and actually all its dependent libraries. And also it's responsible for rebasing, which means to adjust memory addresses to handle some ASLR stuff, and binding, which means to actually resolve and link symbols across different binaries and dynamic libraries, like in import and export. And then he called the initialization functions and the constructors, like load method of Objective-C, of those dynamic libraries. Only after he finished load, rebase, bind, and initialize each dependent dynamic library, he transferred the control to the app's entry point and actually execute the application. Two of the important components of dyld are dyld and libdyld. Dyld is actually the dynamic linker that loads and links dynamic libraries before the app is started, and libdyld is a dynamic library which provides APIs to interact with dyld at runtime. Those APIs are very usable and important and gives us, as a researcher and developers, the ability to not only interact with dynamic libraries at runtime, but also to do some other cool stuff that we can see. And this is actually the main flow of dyld. It's taken from its source code itself. Dyld is open source, so any one of you guys can actually open and read the code. And I want to start over it. So at each process creation, actually the kernel loads dyld and execute the dyld start method, which just set up some registers and then call the start itself, which is the entry point for dyld. And I don't have enough time to cover all the functionalities for dyld, so I just focused the important things for this presentation, like the persistence allocator, which hold the process config class and the APIs. And the process config class are just is a class actually that holds the fixed initial states of the process, like logging and security methods, including how dyld use the dyld environment variables. And the APIs, aka runtime states, are the ones who related to the libdyld itself. It's creating persistence for the API. And then he called the prepare method. The prepare method is the main logic for dyld that loads all the dependencies and bind them together. And after he finished to prepare the applications with all loading, rebasing, binding, and initializing each dependent library, he returns a pointer to the app entry points and actually execute it using the app main method. So I hope you are still with me, because actually now the fun part begins. We will understand how can malicious actors use some legitimate functionalities of dyld for offensive concepts like injection techniques and runtime manipulation to eventually not only avoid detection, but also to be hidden as possible. We'll start with the first technique, which is static load command injection, which is just a way to let us to inject the lc load dylib load command, which is a load command that tells dyld to load a dynamic library. And by injecting the lc load dylib load command, we tells dyld not only to load our malicious dynamic library, but also dyld run the constructors. So as we can see, a simple implementation using OP tool to inject the lc load dylib load command with the path of our not so malicious dynamic library into the target binary, which I choose to be the main test app. And that's it. That's all we need to do to statically injected dynamic library. But it's not enough, because, okay, we are able to inject code and run dynamic libraries, but we want to be more hidden. We want that a security researcher that will open the binary with Mach-O View or IDA Pro will not just find some random dynamic library that is not familiar with. Therefore, I want to cover another mechanism, which means actually that how dyld is located and find dynamic libraries at runtime. As if you remember from the previous slide, I added the not malicious dynamic library with some path. The path can be also the original folder and location from disk or in the shared cache. I'm not going to talk about the shared cache. It's way out of the scope of this presentation. But it can be a hard-coded full path or a relative, like the @executable path or @r path. The @executable path points to the actual application bundle folder, and the @r path points to the lc rpath load command, which specified a runtime search path for locating dynamically linked libraries. In addition, dyld gives us many environment variables and we can use it. For example, the dyld path environment variables that actually tells dyld to look at dynamic library in another folders that you can set. And therefore, we can hijack dynamic libraries by only parsing the target binary, finding a library that is set with a run path, like rpath or executable path, and make sure we have writable permissions, and replace replace the existing library with our malicious one. And that's it. The hijack is completed. But it's not enough, because hijacking in this way may cause a lot of effect about the application, because you actually decide to replace existing dynamic library and you don't know what it affects on the application. And sometimes you don't have writable permissions to the folder the dynamic library is located. And for this, we can also use dynamic hijacking. By using dynamic hijacking, we are just setting the path-related environment variables and tell dyld to use the path override method just to look at dynamic libraries at runtime in a different folder than it's located in the binary itself. But again, we are not solved the main problem, because also here we're still replacing existing dynamic library. Therefore, we can use dynamic injection. Dynamic injection is actually a way to set dyld insert libraries environment variable to load a library before any other dylibs. It's quite similar to the LD preload in Linux, and this is a great technique to inject dynamic libraries at runtime without the effect of affecting the application itself. And a usage of this technique can be found also at dopamine roothide, which is very, very powerful jailbreak. There we can see that they use this technique to achieve persistence by injecting the launch dhook library directly from its constructor to ensure that launch dhook dylib will always re-injected after reboots. Why this persistence is work? Because, as I said earlier, dyld, when it's load the libraries and executables, it not only load, but also run the constructors and load methods. So this make the dynamic library that of launch dhook always execute. In addition, at launch dhook, they call the init spawn hook method, which set a method swizzling on POSIX spawn function. POSIX spawn is like fork and exec. So if we dive into the spawn hook method, we go to the spawn hook common that actually inserts the system hook dylib into all binary spawned using the same technique, using the same dynamic injection with the dyld insert libraries. So that's how it be done in dopamine roothide. And it's not enough for us because, okay, we find a way to inject our dynamic library. But what now? We want to also avoid detection, and we want to do some runtime manipulations. Therefore, our journey continues with dyld feature called interposing. Interposing works by actually adding a section called the interpose section, which contains a tuple of replacement method and a replace. And dyld know how to take any call from the replace method outside of our dynamic library and replace that call with our simple implementation, with our method. And of course, this functionality have to be done from the prepare method, which is the main logic for dyld. And as you can see, dyld build the interposing table before doing some fix-up and bindings, because you need to know how to assign addresses between different libraries. And then you do the binding and fix-up. And there you go, and interposing. And a usage of this technique you can see also at dopamine roothide from the system hook dylib, which is, if you remember, the one that was injected before. And there they set many interposing, they call this hooking, on many functions like the execve open, dyld open, ptrace, sandbox init, and more. For example, the ptrace hook is actually there to allow them to apply debug flags when they need, and to make sure that they be able to debug the process. And the execv is there to control the process launch. And another cool hooks that they can do to control the functionality and what is going to happen. All this from the system hook dyld itself. And if you come back a little bit to the beginning of the presentation, when we talked about the relationship between dyld and libdyld, and I want you to introduce to you a few dyld API methods that are being used among both researchers and developers, and also malicious actors, to getting information about mapped and loaded images at runtime. For example, the dyld image count method returns the number of loaded images, and the dyld get image name method returns the name of a given library by getting a specific index. In addition, dyld gives us the ability to install a callback functions, which will be called by dyld whenever an image is loaded or unloaded. So a lot, and much more, of course, that you can use to get in information about dynamic libraries at runtime. So, for example, if we come back to the first code snippet from the beginning of the presentation, we can see there is an iteration, a for loop, over all the loaded dynamic libraries using the dyld image count method. And there we get the specific image name by using the getImageName method, dyld API method, with a specific index. And after iterating another loop, a for loop, and comparing the specific image that we get previous with something that looks like a list, it gets the J as its index. So it looks like a detection where the security researchers may iterate all loaded libraries and check if a specific library is already loaded. And of course, if we put everything together, we can see how malicious dyld can avoid detection. For example, I created a simple two implementations, the my dyld image count to return only one as the number of all loaded images, and the get image name to return only the first loaded image, which mostly is the main app. And when setting the interposing on those two methods, dyld provides us the ability that each call to the dyld image count and image name outside of our dynamic library will actually move and call our implementation. So the specific library that checks if our malicious library is loaded or if other dynamic library that may be malicious is already loaded, it will not find us. It will not find us. But it's not the end, because obviously you probably guessed right. If you take a look at the library itself that define the static interposing using the specific interpose section, if you inspect the binary itself, you can find a library with interposing section, which may be a red flag or something that the security researcher wants to know. So dyld provides us another API, the dynamic interposing, that only by setting the dyld interpose tuple with a replacement and a replace method, and calling the dynamic interposing method on a specific image, it allows you to install an interposing on those methods. So no related sections will left in the binary, like in the static interposing and in the dynamic interposing. And we talked a lot about the offensive point of view, but now let's take a look from a defensive position. What dyld gives us as a researcher or a developers for debugging and improve our research abilities. And if I need to summarize it in 2 words, it will be environment variables, and a lot of them. A lot of dyld print variables that gives us meaningful information about all the loaded libraries and constructors and segments and sections and permissions. Yeah, that's what's good. Okay, so a lot of dyld print environment variables that dyld gives us and provide meaningful information about loaded and dynamic libraries at runtime. For example, let's take a look of how we can use only the dyld print segments, initializers, and libraries to inspect and actually find dynamic libraries that related to the substitute jailbreak in all the stages of mapping, loading, and initializing. So for example, here we can find the substitute loader dylib, or at the top of the slide you can see the lib substitute dylib itself. And in addition, we can use the dyld print searching to actually trace dylib hijacking. The dyld print searching variable tells dyld to log out each actually path that dyld look dynamic libraries at. So if me as a security researcher, I'm walking around and find and run up my applications that I expect to find dynamic library in a specific location, and if I find it in a different path and folder, it may be a red flag that something happened in my device. And yeah, it's maybe a good thing to understand and to be familiar with as a researcher, to know that we can use it also. So a word before finished, I want to say a word about us, about Appdome. Our mission actually is to protect all mobile apps, Android and iOS, and the users from threats and potential risks such as injection techniques, compromised environments, and debugging. Part of them we saw today, and many, many other we haven't. I invite you to come to visit our booth. I will be there to talk more and ask more questions. We are waiting for you. Thank you very much, guys. Any questions or something? Okay. Thanks.